Okay, we should be recording now. If anyone on Zoom, anything happens, let me know in the chat or by voice, because I won't be looking at Zoom right now, but hopefully everything's good to go. So yeah, for today's workflow, I was gonna wanna look at the Anemone plugin, which is a recursive script builder. There's not a lot going on in the plugin itself. This is the page here. This is the top bar. There's only 5 things in each of those 5 tabs. Has about 2 components in each one. And I don't even think we'll touch on the internalized or the utilities today. We'll just look at the first 2, which are the classic and the fast components. And what these allow us to do is create scripts in Grasshopper that the output can then become the input again, and it can build upon previous completed work. So normally with Grasshopper, you're not able to ever do this. If we were to try to plug the output of a component back to the input of a component that flows before it down the line, it would throw an error telling us we can't do any looping algorithms in Grasshopper. So this component gets around it, and we can do some fun things with it. And I'll show a couple examples here before we get started. We'll see if we'll make it through both today. We might not, but I'll definitely be sharing both by the end of this. So let's see. Okay, so this first one here just creates a pretty basic tree structure in Grasshopper, and the only inputs that we gave it are these 3 lines right here, which we'll create in a second. Using these 3 lines, we're able to find the endpoint of each of those lines, which is right here. And then we can also find the direction that the curve is going in, which is this section. And then we can duplicate, let's back this up. We can duplicate the input onto the ends of each branch with as many iterations as we want. So right now with 0 iterations, we've only gone a single step. And if we keep pushing this, we'll copy and paste basically with how this script is set up. The branches onto every single endpoint over and over and over again. We're also scaling them down each time, which is why they're getting smaller as they branch out more. And we're just adding on more data to the output of each one. So we can also see them go kind of quickly right there. So that's the first one, little tree structure. And it'll update in real time if we change any of these inputs as well. So if I move one of these branches, it'll also change down the line how everything else is looking. So one tiny change in the beginning will affect everything else and give us very different results. Now it's like very, very flat. That's the first one we'll look at today. Both of these are not that big compared to stuff we've looked at before, mostly because we're basically copy and pasting the same stuff a lot with the script. So the second one here is kind of this random growth algorithm in space. So we can see we start with, I have a couple of shapes that I gave you here. We have a box, a dodecahedron, and icosahedron. So we can start with either of them. Right now we have the dodecahedron, which is a 12-sided hexagonal shape, I believe. And with this one, basically what we're doing is grabbing this first curve, finding a random face on it, and then adding another one of the shapes onto that face. So over time, it'll keep doing this iteratively and grow out in a random direction. This script is pretty basic how it's set up, like it's just completely random. There's nothing guiding it as it grows. But we could go in here more and set more rules over time to maybe prioritize growing a shape in a certain direction. If you had a light source, maybe you could tell it to, with a greater kind of random value, like it would grow more in that direction than another one. So we can give it more inputs like that, but it's not really like emulating life too well because there's only very, very simple rules. But with more code between these 2 inputs and outputs, we could have a lot more going on, basically, but it would get quite complicated there. So yeah, going back into what you all have. So I started with this simple point. And the first thing we'll do for this first workflow is create those 3 input lines and then plug that into Anemone and see how that all goes together. What's it saying?
It's not supported.
How did you install it? Did you unblock it and everything?
Yeah.
And you put it in the components folder?
Yeah. What's the first? No, we always do one. Okay, so I got all first. Could apply. Okay, this, yeah, that's probably fine. Okay.
Yeah, and then just restart it, and if it's still not working, then it's a weird issue. But okay, so the first step here is a lot of copy and paste. So I'll set up one thing and then we'll copy it 2 other times. Basically, we'll just create 3 more points. Let me actually hide all this to make it easier to see what we're doing. And we'll just have the top construct point turned on right now. So with this one, I'm going to create another construct point. And we'll add sliders to each of the X, Y, and Z inputs to set up full control over this point. And then we'll duplicate it 2 more times to get 3 points total. And then we'll basically connect this origin point to the 3 points to make the lines. So pretty simple. We'll start with sliders. You can have whatever domain for the slider you want. I'm just going to do, say, -2 to +2. An okay range. It can be as big or small as you want to really change how it's looking. Still getting that error?
Yeah.
And you unblocked it and put it in the components folder and then restarted?
Yeah.
And you have a Windows computer, right?
Yeah.
Interesting. Yeah, I've never seen that here before on the startup. And you're putting it in components folder. Oh yeah, you have to drag it. If you just double click it, it's fine. Just drag it into that folder with like pufferfish and other stuff. Or you could copy it and paste it. As well. Yeah, sure. Okay, so I'm going to continue copy and pasting to fully set up this construct point. Okay, so this is the most basic thing, just having these sliders set up. So this works. One thing I can do though with how I set up the sliders right now, they just go by integers. I only have 5 different steps. If you want to have more steps between the points, we could right click on one of the sliders. And when we right click on the slider itself, we have this option to edit right here. And if we go into edit, we can set it, instead of being an integer number, to a real, or a rational floating point number. If we click that, it'll add decimal places to the slider. So now we have a lot more control over that slider. So if that's something you want to do, that's totally fair. If you want to do that, just copy and paste it again, have all 3 and plug them in. But at this point, I'm just going to copy this whole group 2 more times. No, I tried to push that stick over earlier. I knew it sounded like a trip on it or something. It's just sitting there. It's in a bad spot. Okay, so there we go. We just have 3 construct points with all the sliders on it. And you can set these to wherever you want in the scene. I'm just going to go ahead and like randomly move these sliders around until we have some points spaced out in the rhino scene. I just showed like how to change something to decimal places. instead of an integer number. So you can do whatever you want. Yeah, the inputs are always up to you. Mm-hmm. Okay, so I just have 3 points above the origin point, kind of spaced out. You could also do them below the origin point. Up to you. It'll look less like a tree if they're below the point, but could also be pretty interesting. So at this point, once you've set up all of the 3 points with the origin, we'll just create a line between all of them. So that's not the component. So we'll need the line that has the 2 points of input. So not the parameter, but the actual operator itself. So with this line, I'll plug in the origin point to A first, to just make it easier to work with. So once the point is in A, we can just duplicate this component 2 more times, because we'll be plugging in points we just set up into all of the B's, but the A will be staying the same. Okay, so once we've duplicated it, we'll just go ahead and plug them all into B, and we should have 3 lines showing up in Rhino connecting those points together. If you have them going other directions, then just straight down to the origin, you probably switched how the wires are connected. So they should all be going from the origin in A to the individual points in B. So once we have all those 3 lines, we can simply merge them together, because that's all we need for the input here. We'll go into Anemone with this merge right after this. Okay, so once they're all merged together, we'll come up to the Anemone tab in here, and under Classic, if we drop that down, we have 2 options. So we have loop end and loop start. We'll just want to grab both of those because they will be plugged into each other to create the loop. So pull these both onto the canvas, and we can space them apart for now. We'll be working for the rest of this workflow in between these 2 components. So this is where all the operations will happen in the looping algorithm. But the one thing we do have to do to both of these, the reason why they're both orange right now, is because they're not connected together, so they don't know who they're talking to at this point. One input / output that's special on these is this little caret, greater than less than sign. If we grab from either start or end and just connect the 2 greater than less than signs together, we'll get a dotted line going in between the 2. And now both of these components are connected together, so they know who they're looping back onto.
Hey RJ.
There, but it doesn't matter. Yeah, what's up?
How do you get the names above the boxes?
Yeah, so the names above boxes is a plugin called Sunglasses,
Darn.
which just automatically draws names on top, which is nice.
Okay.
Yeah, I'm doing that mostly for you all to, if you want to search afterwards, I put it on the canvas, you can still see the name with the icon. Yeah, if you wanna get that, it's just called Sunglasses. I have another one called I forget the other one's called. But I have 2 that do the same thing.
It's all good. I didn't know if it was a setting or something. You're good.
Oh yeah, special, but yeah.
Okay.
Both
cool.
Yeah.
Thanks.
My way. Yeah. Do you have the Anemone tab? The little A right after display. Okay, it might just be like an unblock thing. If you have it in the folder and everything, it's just not showing up. Could be what's happening. Okay, so yeah, at this point, if they're both connected together, we should be good to go to start setting up the rest of it. So right now we have this The reason why I merged is because we have a single input coming in. With Anemone, we'll always want to make sure that we have the same number of D inputs as outputs. So we can zoom in here, and if we want to have more things coming in, we can add. But if they're not the same on either side, it'll give us a bad red error. So I merged them all together just to keep this simple right now. So we only need one input at the moment. So we'll keep that with D0. The merge will be the first actual data input. So we'll plug that into data line 0 right there. And with that plugged into the data input, we have 2 more inputs that we'll need to fulfill before we get started with the rest of it. So the first one is the number of repeats, or the number of looping steps that we do, and then a trigger if we want to restart the looping. So when I showed the example a second ago, we could see it building on itself really quickly. It was going up to the number of loops that we have. So let's see. So with n, we can just use a number slider for that. So you can make the number slider however big you want, but I always try to start at 0 because 0 loops is the least amount of loops we can have. But be careful with the upper bounds, because if you do like 10,000, your computer will just try to die doing 10,000 steps, building and growing on itself every single time. So for right now, I'm just going to do like 0 to 10. Keep it quite constrained. With the tree as well, if we have 3 inputs, every time we do a loop, this 3 is going to turn into 9 because it'll put 3 on all the 3. So we're basically multiplying, yeah, exponentially by 3 every single time. So it'll get very big very quickly if we have a lot of loops for this. The second workflow that I showed, where the kind of dodecahedrons just stack on each other, you're adding one thing at a time, which isn't crazy. But this one can get really bad on like 11 steps if you just go from 10 to 11. So be careful right there. So I'll plug in 0 to the number as we'll start. And then for the T, that's the reset button, we'll just grab a button. We can bring in as well and connect that to the toggle or the trigger right there.
So that's basically like it will start looping grow and we'll watch it grow, and then we need that button to go back to 0.
And it'll start growing again as soon as you hit it. We could do a Boolean toggle if we want an actual start and stop, because we could set it to be 0 forever. With the button, it's going to be, I think when I press it, it'll be true for a millisecond just to restart and keep going. So, up to you if you just, but also if we put it at 0, it'll stop as well. So.
So could you put it to a certain point? Like you say, oh, I like the way it looks at 8.
Yeah, if you played a whole thing and you said I liked it at 8, you would just take the slider down to 8 and then redo the simulation and grow it back to 8. But you can't, I guess you could go back in steps, and we'll see at the end how the data is coming out at the end, because with this one, it'll be kind of collecting the data over time in a branched tree. So you might be able to select out the branches you want to keep, and the ones you don't can just go away. But yeah, we'll see that in a second here. So at this point, we can build everything that's inside of the Anemone loop. So coming in, we just have lines. And I did this just to keep the input simple, and also the loop back on itself simple. So if we had multiple inputs, like if we had the lines and we had the start endpoints both going into 2 separate inputs, then we would have to also parse that out with the output on the end so it can loop back correctly. With this one data type being the single input, we can simplify the inside. So we know that every time we loop, we'll be given lines again to do an operation on. If we somehow start giving points to D0, it's not going to know what to do. So we're keeping it simple with lines, and we'll extrapolate all the other data types we need from these lines themselves. So the first thing we want to extrapolate from the lines is the endpoints that we set earlier, basically. So if we just take the data straight into this endpoints, we'll get 2 points for every single line. Currently, we have 3 points down at the bottom here that are all have the same numerical values in space. But there are 6 points showing here. So we should have 3 start and 3 end. So once we have the points on each end of the lines, we'll also want to find the direction that the lines are facing in so we can correctly orient the 3 branches with the next step. So we can use the evaluate curve component. And this one will allow us to find, 3 things about the curve. So the point that it's on, the direction, and I think the angle that it's also moving at, yeah. But right now, since we only have a single straight line, t, which is the tangent, so basically the vector that the curve is pointing, is the only piece of data that we'll need for this. So we can also plug the data into curve as well, because we have curves coming in. The important thing to do here with this is, again, with curves and finding values on curves, one thing to do is right-click on the C as it comes in, and we have this option here for curves, which is reparameterize. So the easiest way to work with this is to make sure every single curve has a domain, basically a start at 0 and an end at 1. Since all the curves will probably be a different length, because with the sliders we just set them to be different lengths, they'll all have domains from 0 to an arbitrary value. So reparameterizing it will tell us that the start is always 0 and the end is always 1, which makes it easy for us. So once we've reparameterized it, I'm going to create a panel. So again, that's 2 slashes. And I'm just going to set that at 1. So since we reparameterized it, if we set a value of 1 into the lowercase t here, that's setting the, let's see what it's called specifically, the parameter on the curve that we want to find information for. So since we reparameterized it, we know 1 is going to be the very end of the curve. So we plug that 1 in. Now we're finding the direction at the end of the curve. So we'll know when we put the next one on, it will always be going the direction that the previous curve ended off at. So if we look on T here, we can see we have 3 vectors that point that direction. We can visualize those vectors with a vector display component. This isn't necessary for the script. You can also see this component does not have any outputs, which is pretty rare, but there are a couple like this. Basically, what this one does is all it is useful for is visualizing something in the scene. It's not actually adding anything. With this, the visualization vector component needs a point to start at and also the vector. So we have those 2 from here. So we can see highlighted in green here the direction for each of those 3 curves. So that's set up correctly. Okay, so the next thing that we'll do is to change the scale of the lines as they come in based on what step we're on in the looping algorithm. So for this one, I want to scale each of the sets based on the starting point before I orient them onto the end of the previous line. So in order to do that, we have, let's see, we have 3 starting points. So when scaling, I'll just grab the scale component first and we'll build up onto this. But we will be scaling the curves themselves based on their group start point. So we have all those start points coming out of S. But in order to scale this as a whole, I only want to scale it around a single point. So in order to do that, we'll have to get rid of 2 of these points in this list to make that happen. There's a couple of different ways to do that, but the easiest way, might be the easiest way, is to just, let's see, with Kangaroo, we have this remove duplicate point command. So you can just start typing in duplicate, and it should be up there with Kangaroo. And what this will do is it'll just find or take every point in the list and delete it if it's really close to another one. In this case, the start points will always be exactly in their neighbor's position. So if we were to remove duplicates, we'll end up with a single point coming out. So that's nice for what we're doing here. Okay, so this point is going to be the center point of scaling. So that can just go right into C, for the center of scaling for this component. We'll also need the geometry to scale, which in this case is going to be the curves themselves. So that's just the data coming out of D0 again. And for this, we'll also need a factor of scaling. So another benefit of using Anemone right here is we have this other output that's not the loop command, it's not the data, but it's just the count of how many times we've done the Anemone plugin. So right now it's at 0 because we've only looped a single time, but as we loop more, this number will build up. So we can use this number to become the scaling factor. So every time we move up one, we can scale down a little bit more every single time, until we hit 0 or nothingness. In that case, with this counter, it's just going to go up by an integer of 1 every single time we do a loop. So that's not going to really help us scale down every single loop. So we'll have to construct a little math components to give us a value that gets smaller every time this counter number goes up. So the first thing we'll do in order to grab that is I can convert this counter. Since we only have a slider from 0 to 10, we can start by multiplying the number that comes out of here by 0.1, which will give us a decimal. And then we could just subtract it by 1 to give us a range in between 0 and 1 for a good scale. So I'll grab this multiplication component. And then we'll set a panel right there of 0.1. And we can plug that into either input because multiplication is fine for that. So with 0, again, we're going to get a number of 0, but as we loop more, this number will actually become important. So let me just loop once. Okay, I don't think it'll actually do anything until we plug the rest of this in. But the next thing I'll do is just so we make sure that this is starting at 1 and then going down as we add more to it, is to get a subtraction value and another panel of 1 in this case. So now at 0, the number we have coming out is 1, which as a scaling factor means nothing will happen. But as we start counting up more and more, we'll start getting 0.9, 0.8, 0.7 as the numbers go up. So we can use that value to go into the F, which is the scaling factor of the scale. So with that, we have all the data that we need to start orienting these 3 lines onto themselves again. And for that, we can use this component called orient direction. There's a lot of inputs for this one, but it does help us out a lot. Basically, what this one will do is it'll take input geometry and it'll need 2 value inputs for the before and then 2 value inputs for the after. So it'll need a point and a direction for where we're starting from and a point and a direction for where we want to end to. So currently, we have the point of the original 3 curves, and we also have the point and the direction of the ends of each of these lines. So we have all the data we need to fulfill this list here. So the first thing we'll do is plug in the geometry. So we can use the scaled factor of the 3 lines as the geometry. So we'll just plug G into G for this one. And then we know the starting point, which is just this point at the origin down here. So we can use the duplicate point component as our start point, which will just be this lowercase pa. So point A, which is the reference point. So for the starting direction, in this case, we don't have really a starting direction with just these 3 vectors right here. What we can do to kind of interpolate the middle of all these vectors is to just take an average of the 3. And with an average, that'll kind of give us a curve vaguely pointing up vertically. It'll be different for how your lines are set up. But if we have this average, we can just plug the t, which is the tangent vector at the point, into there. And you'll see on the output, we'll just have a single vector. We can also do the same thing with the vector display here. So instead of having the 3 vectors from there, we can use, say, the start point and this new vector. And you'll see now we have one that's vaguely pointing up. So we can use that as the start, which is the closest vector between all 3 of them. We don't need this. So we'll use this vector into direction A. So dA right there. And then for the last 2, for PB and for point B and direction B, we have those, and those are both P and T from here. So we have the points, which are the 3 points up top, the start point, and you can see things are starting to move up on top here. We also have the direction of B, which is the tangent value from here. So plug that in as well. And now the curve should change a little bit again. So you'll notice at this point, we don't have 3 lines, coming out of every single line from before, which that's because these bottom 2, since we have 3 different points and 3 different vectors, it's taking each line. So line 1 will be going to point 1 and direction 1. So it's one of these, say it's this one. Line 2 will be going over here, line 3 will be going over here, which is not what we want. We want all 3 lines to be going to each of the 3 points. So in order to do that, we can graft these bottom 2 here. So these are the end, so the point to end at and the direction to end at. If we graft both of those, now we have branch 0 will be operating on everything in this list. And then branch 1 will again operate on everything in this list. Same for branch 2 will operate on everything. So now we're moving all 3 points, all 3 curves at the same time, just like this. So we should be seeing that if everything's working correctly. So at this point, we have 3 branches, and each of those branches has 3 curves inside. This panel is not necessary, but we can see we have the 3 branches with 3 curves. So now we've gone from the input curves to these output curves. So with these curves, you kind of have to think differently about how you construct grasshopper scripts at this point, because you'll have to imagine that now all of these curves will become the inputs, and we'll do the same operation onto them again. So building scripts with Anemone can, at least for me, sometimes be confusing because you don't really think about the implications of doing one thing and how that will affect what happens when it loops back on itself again. Keep those words, but for now, everything's set up correctly. So we can just plug the output into the data 0 right here. So that's all set up. So at this point, I'm just going to hide everything except for the final component. And one thing here too, before we actually start looping, because it's not going to work right now, it's just going to show you a single thing as you move the loop slider around. It's not what we want. One thing we'll do before we start looping is to just merge this output here with the curves we started with, so we see all the data that we want. So I'll just, put this first merge into data 1, and then the output of the Anemone into data 2. So we just have everything in this one component, and I'll hide everything else except for that one. So now we have the budding start to our little tree here. And the last thing to do to actually get this to show you everything when you move the slider, because if you see right now, we're just going to get each section of the branches as we move the slider. The last thing to do is on this loop end here, you'll notice at the bottom right now it's saying constant output on the loop end. If we right click on that component, the icon in the center, we have this other option here called record data. If we hit record data, this will actually record every single step in the loop. and not just the last one. So now with this last component selected, so we can see it in the scene, I can go ahead and start moving this slider, and we'll see the data will grow on itself over time and get quite big. I'm probably not going to go higher than 6 because we probably have a lot going on right now.
That one is better.
Yeah. Something we can do to actually measure, how many things we're adding every single time is to use a list length. With the list length, that'll give us a number of how many items are coming into it over time. So let me just make this panel a little bit nicer. So if we flatten everything coming into the list length, then it'll break down all the branches and just give us a straight stream of lines, and then we can count all those lines and get this final number here. So let's just drag this back over here to our slider. Okay, so now we can see at the very first step, we started with 12, and I'll just move up. We have 39, 120, 300, 1,000. We went from 300 to 1,000 with that one step. So yeah, it's really adding on a lot at a time. 30,000. So my little laptop can, just barely handle this. I wouldn't recommend going up for everyone, but it is cool to see it, especially as it grows with the loop. Yep. Yep. Yeah, so since the button is a button and not a toggle, it's always running. So it is nice though, if you move it quick enough, it'll just do the beginning of it and not go through the whole thing. Once you let it go, that's a bad idea probably. Okay. Yeah, it'll just always keep going. So, be careful with how many numbers you have set as well. Yeah, so this isn't a philosophy class, but if anyone was wondering about the butterfly effect, we can go from a small little shape to just a couple different numbers to something like this. And all I did was change one coordinate, so that's pretty cool to see. Okay, so that was the first one. Pretty cool one. We still have about half an hour, so we can take a look at the second one now. Okay, so down below the script we just made, there should be 3 more inputs. I'm just going to look at one for now, but we'll set it up and you can plug in a different one and get a really different output. So you could use any of the inputs that you want. Right now I'm using the middle one, which is the dodecahedron, but the workflow is going to be exactly the same for either of them. It'll just look a little bit different. So with any of these selected, this is the only input that we need for this workflow. So we'll just grab the loop start and end again, and either of the shapes that you select is going to go straight into the data 0 input and become the start to the loop. You don't see it in the file?
Oh, it's just a file.
Oh, I mean, you don't need it. If you have Weaverbird,
Yeah.
Then yeah, it's the platonic
Okay.
dodecahedron. Yep. Yeah, I just grabbed them all from there. And then the cube is mesh cube for pufferfish. Yeah. Okay, so again, with these, we have to connect them together up top in order to get this to work. So just shove those together. Okay, and again, we'll need a button and a slider for the count and the trigger. So I'll grab both of those. This time I'm using a slider from 0 to 100, up to you, but we're only adding one piece of data every time we loop, so it's never going to get to 30,000 like the last one. The shape itself will become data input 0. Again, this is made up of curves, so we're only using curves for this workflow, which I guess, Sarah, if you're doing the dodecahedron, you should be good. But if you're using the icosahedron, it comes in as surfaces for some reason. So you have to convert that to curves first. I think same with the cube. Yeah, this was the script before I exported them for everyone. So you can find the face boundary if you don't have the boundaries themselves. But the dodecahedron is the easiest one. Like this one here. Right now with this one, it just is standard. If you drag the two together, it will be dotted. And these are the Anemone start and end loops.
Yeah.
I mean, if it's something different, it's probably fine. Because all you have to do is connect it and then it just works, at least as far as I know. But the dotted line usually means it's a grafted tree, like it has multiple branches of data together. In this case, it's always going to be null. There's nothing really happening. It's just connecting the two together. So I don't know why they chose dotted, but or not. It's random. But yeah, it does not matter what this is. Okay, so for this one, the way I'm going about this is, let's see. So if we take this one shape, let's bake it in here. So if we took this shape, say the one starting there, and we randomly found, say, this face on the right side as the face we want to apply the next shape to, then what we could do is find the point in the center here, as well as the direction that this face is going. And we could say, based on those two values, we can then, again, orient the shape onto that point in that direction. So it would kind of, come over here and not do that and rotate to fit. Kind of get stuck on like that. So that's the basic idea. And yeah, I did that really badly, but that's what we're going to shoot for. So in order to do that, the first thing we want to do is to just grab the center of each of these polylines. That's the reason why we're coming in as polyline curves. So in order to do that, there is a nice component, and this is just for planar curves, is to use the polygon center component. A lot of the other workflows we've used, the area component to find the center, and you can do that for 3D shapes. If you have the volume of the area, you can also find the center. So right now, since we have flat curves, we can just use polyline center. So if we plug the data 0 into the input here, you'll see we'll get points coming up for all of the curves there. So there are 3 outputs from this, and sometimes they'll be different because it's doing different centers. So, we have the average of the edges, the centroid, and also the average of the vertices. So you could use any of these. They're all technically the center, just a different definition. But for our cases, since we have a nice regular pentagon, all the center points are going to be the same. I believe so. Yeah, they're pretty close together. So doesn't matter which one we use. I'm just going to use the center of the vertices. So with this one, the first thing we'll do is pick a random point. So in order to do that, we do have a component called random. This little orange ballot box here. I think it is. Oh no, it's a cat in a box. Okay, so it's a joke. That's kind of funny. So we'll use this to grab a random number of one of these points. So the first thing to do that is to actually figure out how many points we have. So just like the very end of the last workflow, we can use the list length, which will take the list or everything that's written down here and figure out how many of them there are. So we can just plug the center of the vertices into the list length, and it should tell us we have 12 points, which makes sense because the dodecahedron has 12 sides. So we can use that number as the range here to actually, tell us in what range we want to find a random number. So don't do it yet, but if I plug this into R, you'll see we'll get a domain of 0 to 12, which seems like it makes sense. But if you think about this, as a computer would, 0 is also a value. So technically we have 13 values possible here, which we don't want because we only have 12 things to choose from. So everyone should have the pufferfish plugin because we've used it before. And that plugin has a very nice component, two of them actually, called either x-1 or x+1. If you don't have these, you can just grab a subtraction component and subtract the number by 1. But since that's done really often, pufferfish has this component. So we can grab the x-1 and just subtract the list length by 1 to get 11, plug that into the range here. And now we'll have a number from 0 to 11, which is perfect because the list is starting at 0 and counting up 12 times. So 0 to 11 works for that. Another thing here, using the count again for Anemone. So every time this moves up, it'll change the number, which is nice because with this random component, it has a seed value. So seed means we can change kind of the randomness of it every single time. So if we were just to use this component right now, it's always going to give us a random value of 8.5, which is never going to change unless we change that seed value. So we can use the count itself into the seed here to actually change it based on the count. So every time the count changes, this random value is also going to be completely random, which is nice. So one thing too you'll notice is we have 7.98, which isn't technically picking one. It's kind of in between 7 and 8. But if we right click on the icon here, the little cat, we can just hit integer. And now the random value will always be an integer. So now we're definitely going to select point number 8, which is index, or number 9, which is index 8. Okay, so with that, we can use a list item right here. And list item will use an integer to select a single value. So with that, we can use the random as the I for the index. So this is saying we want the item at index 8. I'm going to use the actual center point from this center point component. So we'll just use that same vertex center into list item. And this will give us a single point that was randomly selected down here on my shape. It might be different for you. I don't know if every grasshopper has its own randomness or if they're all the same randomness, but mine's over here on the negative x-axis, kind of. Okay, so now that we have the point, we'll also want to find the directionality of this face. So we want to figure out, why this face is pointing kind of down in the negative x, negative y direction. Or I guess everything's negative z as well. So we can do that pretty easily. And the way to do that is we'll actually create a surface for each of these planes. So one way to do that is, normally we can grab planes like this. We can grab an XY plane. We can't do much with this because all this has is a single vertex input. So that really doesn't allow us to change directionality. So one thing we'll do is actually construct a plane out of 3 points. So what we can do is take each of these curves and say randomly divide the curves into 3 points. And since they're planar, it doesn't matter where those 3 points are located on the curve. It'll always give us a plane that exists in a planar way with the curve itself. So in order to fulfill these 3 inputs, we'll have to break these curves up. So the stuff coming out of D0 is the curves. So we can divide those curves with divide curve into 3 different points that'll exist on that curve. So with divide, we can use the curves themselves from the data 0. going into C, which is the curve input. You'll see by default, it'll divide each curve into 10 segments, which is not what we want. We want 3. So we can grab a panel, basically, or you can grab a slider, but we never want to change this value because we always want 3. And we'll use that value of 3 to go into the number, which will set the number of segments, which will set the number of points we have on each curve. So now we have 12 branches. Each of them have 3 points on the branch. So with those 3 points, you'll see that now all we have is a single output that has all the points in it. So how do we break that up into actually 3 inputs for this component? We can also do that with a list item. It's a very handy component, can do a lot of different things. So with this list item, first thing we can do is plug the points from the divide. So we have all those branches with 3 points. We can take those points into the L input. And what that'll do on the output, you can see now that each of those 12 branches now has a single point in it. And that's because the default index is at 0. So right now we're just selecting the first point of every curve. And for some reason, those are all placed on the top and the bottom, but it's pretty arbitrary. But if we want to get 3, what we can do is zoom in to the list item component. And we can actually click this plus button here to give us as many outputs as we want. In our case, we only want 3 outputs, so 0, 1, and 2. And we can use those outputs as A, B, and C for the plane 3 point. So zoom in until you see them, and then click the plus button. So with that set up, we have everything we need, and I'll just, slide straight over those 3 points into the 3 points for the plane. And now we'll get 12 planes existing on each of those shapes right here. So they're kind of all random. They're pretty much placed about the first point that was plugged into them. So, they're kind of all centered around that one point that was placed there, which doesn't really matter. All we need is the directionality of the plane itself. So at this point, we can merge the center points up to the normal value or the directionality of the planes. But the first thing we'll do is, right now, these planes are all on 12 separate branches. And these points, there's only one of them. Oh yeah, so, well, it still tracks that since all these are branched, we can't actually select number 8 again, just like we selected this point number 8. So the first thing we can do is flatten these. So they all look like these curves. Because we'll be using the same random value to select plane number 8. So we can just duplicate this list item. So we have 2 of them. We'll keep one as the point from the vertex center, and the other one will actually be a plane selection. So we'll use those planes. I'm just going to go ahead and hide everything we don't need anymore. So now at this point, if we've selected, at least in my case, a random value of number 8 for both the points and the flattened list of planes, now we have everything we need to actually construct the plane that we will use to orient everything around. So with these 2, I'm actually going to construct another plane based on these 2 values. So the plane itself, we can use as a directionality. A plane isn't only directionality, it's also a point. But if you ever want to use it as a vector, you can just plug it in and it'll do the conversion for you. So what I'm going to use is a plane normal. And plane normal has 2 inputs. It has an origin point and a z value basically for the normal, so how that plane is going to be facing. So we have both those values here. They're just kind of in the wrong order. So the bottom one is the point, so that'll be going into the origin. And the top list item is the directionality, the vector, which will be going down to z. And once we do that, we'll see that we've actually created a plane itself oriented about the center. So this one plane contains both the center point and the direction of that face. So we've kind of consolidated a lot of data into a single plane here. Okay, at this point, we have everything we need if we're looking at what we want to travel to. But now we just have to basically set up where we're traveling from. So this could be any point and any plane on the dodecahedron. That should just be the place where we start, so we know how to orient it as we move it. So in this case, I'm just going to grab the first curve from the list. It doesn't matter which one it is, so the first one works. So with that, we can grab another list item with the curves from the data value of 0. So with this selected, it doesn't really matter which one it shows up as selecting. We just want to select one of them. Right now, it's just the first one. What we can do at this point is pretty much just copy everything we did before down here. Because this is finding the plane based on the curves, and we'll just want to do that same thing with the new one we found. So with all this copied and moved up, we don't actually need to find a random value again, because we already know what curve we want to select, just the first one, the arbitrary first one. So we can go ahead and remove the list length, the x-1, and the random from this calculation, as well as the list items from the end here as well. We don't need any of that. We just need the center and then the plane. So delete all this. That's highlighted in green. So take that out. Okay, so now with this more simple setup, we'll take this list item and just replace these two lines with this one, because they'll be taking the place of that. So now we have the middle point of the top curve and also the plane that it exists on. The only reason I'm doing it like this is because the first curve may not always be just nicely on the top. You know, once we start copying these and orienting them, that first plane is going to be something completely random and different. And we can't just use a flat plane to call it flat, even though it is at this point flat, but it could be turning as we start looping. So we want to set up all these checks and balances, so when we start the loop, nothing just breaks on us. So with this setup, we have the plane and we have the point again, so we can plug the point again into the origin and the plane into Z direction. So now we have that oriented plane on the first surface, and then also the plane down at the bottom on the random surface. So with these two values here, we can use a different kind of orient, which orients about two different planes. So there's a lot less input here. We don't need a point and a direction. We can just use a plane and a plane, which, you know, contain points and directions. So again, with this, when we're orienting, we want to use the original curves that are in D0. You know, this will be tracking through the whole loop. We're just going to modify it before it goes back to the output. So with those original D0 curves into the geometry here, we'll now want to set up planes A and B. So we have both of those. We know which plane we're starting at, which is the top one, and then the plane we randomized, which is the one down below in the script. So the starting plane is just A, and the ending plane is going to be B. And you'll see it'll take our dodecahedron in my case, and change the place that it's sitting at right now. You will notice probably that the shape is sitting inside of the other shape, just because when we set up the plane itself, the plane direction was kind of facing inwards. So it's really simple, since that is consistent every single time, because we set it up the same way every single time with code. We can just go ahead and flip that plane. So flip plane right here. before it goes out, and this will solve our issues down the road. So with this, we can just plug the plane from B into the flip plane input right here. And we'll want to flip the Z-axis. So we can just grab a toggle, set it to true, and plug that into Z. So Z is the directionality of the curve. You see we have Z here, and it's just going the wrong direction at this point. So once we flip it, it won't look any different. The plane will still be, the same. But you will notice the color of these lines is changing because we're moving, that imaginary Z-axis to the other side. So once it's flipped, we can just plug it back into B, and we'll have that shape existing on the outer side of the polygon. So now that we have this working, we can go ahead and plug this into DO, which is the output. And again, right click and hit record data so we can see it happening as it loops. And then I'll also go ahead and grab the merge component again so we can merge the first component, which is just the one all the way out here, with the output of the loop. So we just have both things going into one component so we can view them together. So with that set up, we can go ahead and start this loop. Actually, let me roll it back a little bit. So it is looping at this point and it's working, but since I was a stickler for detail when I made this, you will notice sometimes, at least with the dodecahedrons, we won't always get them orienting about the same rotational value as the surface is going on. And you can see these pentagons are not exactly lined up, which makes sense because we didn't even think about that until this point. We didn't think about the rotation of that axis. The plane only shows you the origin point and the direction, but it doesn't tell you about how to rotate each one. So we can go ahead and solve for that real quickly with a couple more components and then re-plug this back into the output, and everything should be working perfect at that point. So I'm going to move this end over a little bit so we have some space here. And with this workflow, we've used this plane to plane orient, but also be using the orient direction from before to actually orientate the spin of the shapes as they orient onto the previous one. So I'm going to grab that component again, so the orient direction with the two circles here. So we'll have to set this one up. Again, the G can be the same as this one because we'll be turning the same geometry, so we can simply plug those together. In order to find the rotation of each one, what I came up with to theorize this, let me roll back one so we can see this one here, is to find 2 points that are close together, figure out what the rotational difference of those 2 points is, and then solve for that by rotating it based on the middle of those two, so we get them both to rotate together. So in order to do that, first thing I did was created 2 vector 2-point components. So with this, we can find the vector, say from the center point to this outer point, and then for the same for the second shape from the center point to this outer point. We can find these 2 vectors, which I'll show really quickly with how those points are lined up. So we'll be using the 2 planes we found before. Actually, for this one. So with this plane, we have the plane that splits those 2 shapes together. So we have the starting shape here and the second shape here that was put onto the first one. And we have this plane splitting them. So again, with planes, we have the directionality, we also have a point. So I can pull out that point just with a point parameter. So if we plug the plane into this point parameter, you can see that we're now getting the point of which those two shapes can rotate around. So once we have that, we'll want to find the points on these curves themselves that are close together that we can then solve for. So the quickest way to do that is to just find all of the points that exist at the kinks of the curves. So with this discontinuity component, if we plug in a curve to this one, it'll give us all of the points that exist where there's like a sharp edge or a sharp, point between two edges. So I'll use two of these components. So I'll just duplicate this, copy and paste it there. And the first one will exist without the input shape. So this is the starting shape here. Let's see. This one, so the starting shape, we'll grab that data, same from D0, put that into the top discontinuity. And you'll see we'll get all the points that exist at the creases of this shape. And we can also use the shape that was oriented. So the second one, also plug that into the second discontinuity there. And now we'll get the points on the second shape as well. So with this bottom one, now we'll want to find the closest point to this rotational point here. Easy way to do that is to, what is it called? Find the closest point component without the S. So this will find a single point that is close to whatever other point we set. So we'll just be simply searching the entire shape for the closest point, which in our case is going to be a point about this, rotational plane down here. So grab that closest point component. And we know we want to, with this first input, this is the point to search from, which will just be this middle point here, search from. So we'll start the search there. And then we'll want to search within all of these points for the closest one. So if we plug those points into C here, so the points to search, we can see that it has found all the closest points to this point here. Currently, it's finding the closest point which within each of these branches here. So, each pentagonal curve has 5 points, and it's found the closest point in all of them, which is not what we want. And we can fix that just by flattening this output here. So if we flatten all those points, out of their curves and all into a single list, then we can search that entire list for the single point that is closest to the point that we're going to rotate around. So that works pretty well, and we have this one point right here on the dodecahedron. So now we'll want to find also the point on the first shape. And to do that, if we do the same workflow, it's going to find, a random point, say we flatten this one as well. And the point it's finding is on the opposite end. And if we kind of rotate based on the 2 points we found, we're not going to get the best result because they're so far away. So I don't want to do the same workflow again, but we still need this other closest point component here because we'll be using both of these. The only thing I want to change is instead of starting the search from the center point as well, since we already found one of the points on a dodecahedron, we can start the search from there and find the closest one to that on the other shape. So instead of having the starting point from here, we can use the starting point from the point we found, just pull that up to here. And now we'll get the point that's right next to it. Now we have 2 points that are super close together that we can now find the rotational difference in between them. So now with this vector 2 point, I'm going to duplicate this one because, again, for the orient, we need the starting point, the starting vector, as well as the ending point and the ending vector. So we have the points here now, so the starting and ending. So we can, let's see. We'll set up the vectors first, and then we'll plug everything into the orient component afterwards. So with this top one up here, this will be the ending vector. So we know we have the ending point here, so we can plug that into B, which will be the end of the vector here. And we'll have this center point be the start of the vector. So we'll plug that into A. And we can't see that, but to visualize it, again, we can grab a vector display, which doesn't do anything, but we'll be able to see the vector that we created. So we'll see it exists right there. And we'll just do the same thing for the other shape as well. So same, it'll start from the center point again in A, and it'll end at the outside edge point right here. We'll just visualize it quickly. So now we have these two vectors. And a vector has a point and a direction, so we can also find the angle difference between the two, which is what this orient component's going to be doing. So now that we have the points and the vectors, we can take the start point, which will just be the point down here on the one we're moving, because we want to move this one. So we'll find this is the starting point, so we'll plug that into the point on A. And we have the vector from that point, which is this one, the one that lines up with that point. So we'll take that vector, plug that into the start direction. And then we'll do the same thing, but just for the other set. So we have this point and this vector. So this will be the starting point into point B. And then this vector is the ending vector, so direction B in there. So now you can see, let me just hide this one and this one. Now you can see the second shape is in line with the one before that. So the vertices are now lined up. So that's perfect, ready to go. So instead of this orient being the final one, we'll now make this orient the final one. So we'll grab this G, plug that into DO, and it'll take the place of the orient from before. So I'll just preview off all of our work there and turn on this final component again. So now at this point, everything's set up, and we can go back and restart the loop. And you'll see now that when we loop, we have that third shape completely in line with the one before it. So now everything's solved for. The location, the direction, and the rotation between the two shapes are all solved for. So now we have perfect matching between the previous and the subsequent shapes. The only thing that isn't solved for is the dodecahedrons do not tessellate perfectly. So there's a little bit of an air gap between the two. But that's just something geometrically that's impossible with the dodecahedrons to tessellate them like this. So if you had a different shape like a cube, which is one of the other inputs, that would tessellate perfectly. And I'll show that in a second, but for right now, we'll just see, this loop grow on itself as we move this slider up. So now I have all the shapes randomly growing in space 100 different times. And this shouldn't be too laggy. Not a lot of stuff's happening. It's just going to take a while for all the shapes to visualize in Rhino itself. We can hit that button again and see it all start from the beginning. So with this setup, every time you click the button, the same thing is going to happen, like the same shape is going to be output, because this count is always starting at 0 and always going up to 99 or 100 in our case. So the randomness is going to be the same randomness for every time you click the button. If you wanted to change that, we could just simply affect the seed from the outside. So we could simply just add a number to it, and now it'll be different, slightly different random every single time. So first it looks like this. If we add a value of 1 to the count, now it's going a completely different direction. Still random, still pretty organic, but definitely very different from the last one. So at this point, that's the dodecahedrons. If we were to change this to the cubes, do that, we can see these cubes and they tessellate perfectly because they're made for that. Cool. So that's that workflow. And if you wanted to make these solid, just as a final thing here, we could just add faces to all of them. So we have this boundary surfaces component. If you want to see them as solid objects in the scene instead of just curves, it's another option there. We'll see it with the icosahedrons at the end. Cool. So that are those workflows for today. It's about 7 p.m. So that's all I had for class. Next time, we'll just be going over more question and answers for your final projects. So, bring more sketches or ideas or grasshopper files, and we'll be able to look over them for those 2 hours of class and hopefully answer as many people's questions as possible. Because we only have 4 or 5 more classes before the end. So we want to make sure we have time to also 3D print if you're looking to do that, or render if you're looking to do that for your final submission as well. So yeah, I'll put out the rubric for the final project as well. Probably here with whenever the video is done as well and up on YouTube. And I'll share that all with you so we can start getting ready for that. But nothing special, just either 3D print a design or render it and then put together the very simple PDF of your project, just like these people did last semester here. Show another one. Yeah, nothing crazy, but just renders, description of what your thoughts were, and then the grasshopper workflow basically. But I'll put out a PDF so you can all read back on that later. But that's it for class. If anyone has questions, I'll be around. But other than that, I'll see y'all next week.
Thanks, RJ.
Welcome.
Thank you.
Welcome. Stop this.